We can start the second talk this morning. So now we have Pierrick Bousseau from Zurich, and he will tell us about holomorphic Floer, and Donaldson-Thomas invariants.
Okay, so thank you very much for the invitation. So my goal today is to present a conjectural relation motivated by physics between two topics. On the one hand, holomorphic Floer theory, which is about the enumerative geometry of holomorphic symplectic or hyperkähler manifolds. And on the other hand, Donaldson-Thomas invariants, which are about the enumerative geometry of Calabi-Yau threefolds, or in physics language about the BPS spectrum of n=2 four-dimensional field series. So the plan of my talk, I will start by some introduction, some overview of known facts about Donaldson-Thomas invariants and their physics counterparts as BPS states in n=2 four-dimensional field series. Then I will talk about an analogy to a much simpler story which involves BPS states in a two-dimensional field series. And the motivational question for this talk is how much can we push this analogy? And the answer to this question will be provided by holomorphic Floer theory. Okay, so I'll start at the beginning by saying a few words about what Donaldson-Thomas invariants, or DT invariants for short, are. First of all, from a geometric perspective. So in geometry, there are integers that I denote as omega gamma of u, which are counts of geometric objects on the Calabi-Yau threefold X with given topology class gamma. So gamma is some discrete topological label which typically live in some lattice z to the n. And these geometric objects satisfy some stability condition determined by some continuous parameter u. And so typical examples are counts of stable holomorphic vector bundles on the Calabi-Yau threefold with fixed chain character gamma for a stability condition prescribed by a choice of Kähler parameter u. Or a different counting problem involves special Lagrangian submanifolds of the Calabi-Yau threefold of given homological class gamma, where the notion of special Lagrangian is prescribed by a choice of complex parameter u. And these two classes of counting problems are exchanged by mirror symmetry for mirror Calabi-Yau threefold. So it is a geometric point of view on DT invariants, the integer counting stuff on Calabi-Yau threefold. Now there is some physics point of view on what will ultimately be essentially the same numbers, which involve n=2 supersymmetric four-dimensional quantum field theory. Such physical theory has a so-called moduli space of vacua, and we'll focus on B, which is a so-called Coulomb branch of vacua of this theory. And in most cases, it will be simply a r-dimensional, isomorphic to r-dimensional complex vector space C to the power r for some integer r, which we'll call the rank of the theory. And physically, at the generic point in B, so a generic point u in B, away from a complex codimension 1 locus delta, the low energy physics is described by some abelian gauge theory with gauge group u1 to the r. And now if you live in such a vacuum, the physics is constrained by supersymmetry. And if you have a state of charge gamma, there is a complex number z gamma of u for the central charge. And you have a BPS bound telling you that the mass of your state is bounded below by the absolute value of this central charge. And by definition, BPS states are physical one-particle states saturating this BPS bound. So there are states of minimal mass for a given charge. And so you have a vector space of BPS states that is denoted by h gamma of u. So in this physics context, u is a choice of vacuum of point on the Coulomb branch, and gamma is a choice of charge. And then you have a BPS index, omega gamma of u, which is essentially some signed dimension of this vector space. Now, what's the relation between the geometric story about Calabi-Yau threefold and the physics story about four-dimensional field theory? The relation between them is via geometric engineering from string theory. If you consider type 2a or type 2b string theory on the Calabi-Yau threefold, you go from 10 dimensions of the string theory to 4 dimensions, transverse to the Calabi-Yau, and you get some n=2 four-dimensional theory. And under such, so you get some relation between the enumerative geometry of X, so the DT invariants, and the BPS indices of the four-dimensional theory. And in this correspondence, the geometric notion of stability, this parameter u, is related to the point on the Coulomb branch of the four-dimensional theory. And something which would be important that maybe already implicitly assumed in some of my notations is that from now on, when I talk about n equal to four-dimensional field theory, I really mean UV complete quantum field theory, so without gravity. So no supergravity, really global supersymmetry. And geometrically, it means that we are talking about non-compact Calabi-Yau threefold, not compact Calabi-Yau threefold. Okay, so now I will say a few words about DT invariants or BPS states. So from now on, I will use the two words more or less interchangeably. So the most important factors is number, omega gamma of u. By definition, they are function of u, the stability parameter from a geometric point of view of the point of the Coulomb branch from a physics point of view. And they're integers, so typically they are locally constant. When you move u, your integer remain constant. But across real codimension 1 loci in the space B of values of u, so across this codimension 1 loci called walls, these integers omega gamma of u, these BPS indices jumps in a discontinuous way. And these jumps are controlled by a universal wall-crossing formula, the Kontsevich-Soibelman wall-crossing formula, which tell you that if you know all the full BPS spectrum on one side of the wall, then there is an explicit way to recover the BPS spectrum, full BPS spectrum on the other side of the wall. And here I draw a picture of maybe one of the most famous example of four-dimensional theory with n equal to supersymmetry, just pure SU2. In this case, R is equal to 1, so B is just a complex plane. Delta is just 2 points. And then there is a single wall which is drawn in red on this picture, and which forms some kind of cycle. And inside it, the BPS integers or DT invariants have some value. Actually, only finitely many of them are non-zero. But outside this cycle, these BPS indices are different. And in fact, infinitely many of them are non-zero. And when you cross this red line, you can apply the wall-crossing formula to relate what happens inside this cycle and what happens outside of this cycle. So an object which is essential in the understanding of n equal to four-dimensional series and which will be also essential for our story is the so-called Seiberg-Witten integrable system attached to this four-dimensional theory. So one way to define it, I will denote it as by M, is as a Coulomb branch of the theory on R3 cross S1. So my original theory was living on R4 on a four-dimensional flat spacetime. Now I view it on R3 times cycle. And so you get a new Morley space of vector M. And by supersymmetry, it is some hyperkähler manifold of complex dimension 2R. It has a structure of complex integrable system. It has a natural map pi over this four-dimensional Coulomb branch B. And so physically, if the S1 is very small, you get some three-dimensional theory, which has low energy, is a three-dimensional sigma model with target this hyperkähler manifold. So it's hyperkähler, so there is a twistor sphere of compatible complex structures. There's a quaternionic triple IJK of compatible complex structures. And when I say that pi is complex integrable system, it means that it is a holomorphic map for one of these complex structures that I denote by I. And for this complex structure, the fibers are abelian varieties of complex dimension R. But for different complex structures, the one I denote as J theta, which has linear combination of J and K, these fibers are special Lagrangians. And so what's the relation between the geometry of this Seiberg-Witten integrable system and the object I introduced previously, the possible charges for BPS states or the central charge? So the important point is that the space of charges, so the place where gamma lives, can be identified with pi2, so the second homotopy group of this space M relatively to one fiber of this map. And so this group has a natural map to H1. So H1 of the fiber is just a torus, so it's just Z to the 2R. And this Z to the 2R is a space of electromagnetic charges. And the kernel of this map has to do with flavor charges for BPS states. So the point is that possible charges for BPS states have to do with gamma in this group. And then the value of the central charge is given by the periods of the holomorphic symplectic form omega I. Okay, so here just a picture for the pure SU2 gauge theory of a complex integrable system. In this case, it's just a family of elliptic curve over a one-dimensional complex space. And just to make connection with something mathematically concrete for some particular class of n-2 four-dimensional theory, this Seiberg-Witten integrable system is the same thing as the Hitchin integrable system attached to Riemann surfaces. And the last thing I would say in this kind of very quick overview is that there is a deeper connection between the BPS spectrum of the theory and the hyperkähler geometry of this Seiberg-Witten integrable system. More precisely, it was shown by Gayotu, Moore, and Nansky how from the data of the BPS spectrum at any point of the Coulomb branch, we can use this data as input to reconstruct the hyperkähler geometry of M, of the Seiberg-Witten integrable system. And in this story, the row crossing formula for the BPS invariants, for the BPS indices, translate into some of the consistency of this reconstruction of the hyperkähler geometry. So this first part was a very quick overview saying DT invariance has to do with counting geometric objects on Calabi-Yau threefold. From a physics point of view, it has to do with counting BPS state in a 4D theory with n=2 supersymmetry. And to this 4D theory, there is this wall crossing phenomenon for these BPS invariants. And there is this remarkable hyperkähler geometry attached to it, the Seiberg-Witten integrable system. So from now on, I will talk about some analogy between this story and what is in fact a much simpler story, which is also a wall crossing story for BPS states, but now in a two-dimensional field theory, no longer four-dimensional, two-dimensional, and with n=2 supersymmetry. So before I was in 4 dimensions with n=2 with 8 supercharges. Now I'm in 2 dimensions with n=2, so now we have 4 supercharges. And mathematically, there is a very large class of examples of such a thing, and which is in fact very concrete and much easier to describe mathematically than the expected mathematics, which would correspond to a rigorous description of a 4-dimensional theory. So mathematically, we're just talking about the Landau-Ginzburg model, simply the data of P, a Kähler manifold of some complex dimension n, and W, some holomorphic function on this Kähler manifold. And let's assume that this holomorphic function is Morse. It has non-degenerate critical points. And typically, for simplicity, let's assume it has finitely many critical points, Zi. So Zi are finitely many points on P, and they're the critical points of W. Then this two-dimensional field theory story, this Landau-Ginzburg theory, is essentially a version of Morse theory. So if you fix an angle theta, you can consider a real part of W. So W is a holomorphic function. And if you take its real part, you get a real valued function. And more generally, you can take real part of W rotated by an angle theta. So you can consider a real part of exponential minus I theta W. And this thing is a real valued Morse function. And so you can just do Morse theory. So its critical points are the same as the critical points Zi of the holomorphic function W. And because W is holomorphic, you can show that all the critical points have the same index n. So generically, you do not expect any gradient flow lines between two critical points of the same index. But for a specific value of theta, if theta is equal to the argument of the difference of the critical values between two critical points Zi and Zj, then you can show that you can have gradient flow lines connecting these two critical points. And you can define mu ij, a proper count of these gradient flow lines between Zi and Zj. Okay, so mathematically, it's relatively concrete. You have a Kähler manifold, some holomorphic function. You look to see the real function obtained by taking real part, and you count gradient flow lines. And you get some numbers, mu ij, which in the physics language are two-dimensional BPS indices. And there is a wall crossing story for these numbers. When you vary this function W, these numbers might jump. And there is some wall crossing formula, which was derived a long time ago by Cecotti and Baffa. In the physics context and in the mathematical, and in some physics version of essentially the Picard-Lefschetz formula in mathematics. In fact, you can do better. So here I just describe explicitly what are the 2D BPS indices. They are simply count of gradient flow lines. But you can do better. You can define vector spaces of BPS states, Hij, and they're again defined by Morse theory construction, but somehow a more elaborated one, which is somehow infinite dimensional Morse theory construction. So you consider the space of paths. So you fix two critical points, Zi and Zj, as on this picture. And you look to the space of paths connecting these 2 points. So you look to the blue lines on this picture connecting these 2 points. So this space of paths is some infinite dimensional manifold. And on this infinite dimensional manifold, you consider some functional given by this formula, essentially by integrating over a path, one form, which is obtained by taking a primitive of a Keller form perturbed by something involving W. And then you apply Morse theory to this infinite dimensional setup. And so, in other words, you construct a complex generated by gradient flow lines between Zi and Zj. So this kind of blue curve on this picture. And then the differential is given by gradient flow lines in the space of paths. So it's given by count of appropriate planes in the Keller manifold P. And there's planes which are so-called zeta instantons. So they satisfied a perturbed version of some holomorphic curve equation. So by essentially looking at gradient flow lines and counting these almost holomorphic planes, you cook up a complex, you take its cohomology, you get a vector space Hij of two-dimensional BPS states. And the BPS indices μij, you recover them by taking some kind of signed dimension of this vector space. You can do, in this two-dimensional story, you can even do better than looking at spaces of two-dimensional BPS states. You can construct a category. So I call brain the category of supersymmetric brains of this two-dimensional theory. And mathematically, it is a so-called Fukaya-Seidel category of this Keller manifold P equipped with this function W. So which was originally defined in a very symplectic way by Fukaya and Seidel, but which can be defined, which is conjecturally can be constructed using similar Morse theory techniques as the one I've just described. It's a story which has been developed by Addis and Gayotomo and Witten. Now I come to the analogy between this two-dimensional story and the four-dimensional story I was talking about before. So in this analogy, in 4D, add these charges gamma living in a lattice, which are geometrically the topological classes of the objects we're counting on the Calabi threefold of the charges of the four-dimensional BPS states. So these things are analog in two-dimensional to the critical points of the function W. The values of the central charge are analog to the values of the function W on these critical points. And the 4D BPS indices are analog to the 2D BPS indices. The space of 4D BPS states are analog to the space of 2D BPS states. And here I put a question mark for what the 4D analog of the 2D category of brains should be, and I will come back to that at the very end of the talk. And so this analogy has been observed by many different people, in particular, both, so the 2D wall crossing and the 4D wall crossing are different, but Kontsevich-Soibelman explained that you can put them into the same algebraic framework. They are both examples of wall crossing structures, but with different algebraic inputs. So they look similar. And actually, this analogy is also an important motivation for some recent work of Bridgeland about the geometric structures that you can construct out of the data of DT invariants. But in this talk, I want to ask the following question. So is it more than an analogy? So is it a true correspondence? So concretely, can we find a Landau-Ginzburg model P and W with two-dimensional BPS states to cover the four-dimensional BPS states? So in its simplest version, the answer to this question should be no, because in the simplest picture of a two-dimensional story, there is finitely many critical points, and there is no hope to match these finitely many critical points to the lattice of possible charges in the 4D story. So if you want this correspondence to make sense, you need at least W to have infinitely many critical points corresponding to the charges in 4D. And what we will show is that in our proposed answer for this question, we'll need to consider some, so there will be a positive answer to this question, but with a caveat that P will be infinite dimensional. So just a physics reformulation of this question, you have some n equal to 4D theory. The question is, can you cook up n equal to two-dimensional theory such that the BPS spectrum of this 2D theory exactly match the 4D BPS spectrum? And one motivation for this question is that the 2D story, the structures there are much simpler than the one in the 4D story. So if you are able to do that, you might be able to learn something about the 4D story. And so in the remaining part of the talk, I will try to give an answer to this question. And the answer to this question will be given by so-called holomorphic Floer theory. So in the description of the two-dimensional story, I review the story of a Landau-Ginzburg model, mathematically Keller manifold, a holomorphic function on it. And then you can look to critical points of the function, then gradient flow lines between critical points, and then these kind of holomorphic planes are symplectic to these flow lines. And out of this enumerative geometry, you can cook up two-dimensional BPS indices, BPS states, and ultimately a category. And some very general idea is to take this setup and try to make sense of it for infinite dimensional Keller manifolds P. So this idea has been actually applied in several examples. So for example, if you take P as a space of connections on a three manifold for a complex reductive group, and if you take W, some complex valued Chern-Simons theory, and if you run this formal story, you get essentially the Kapustin-Witten story, which was related to the first talk of yesterday. So holomorphic Floer theory is another example of this general idea, where P will be some infinite dimensional Keller manifold obtained as space of paths between two holomorphic Lagrangians inside the holomorphic symplectic manifold. And W will be a holomorphic action functional on C space. So usual Floer theory is about the C-infinity symplectic manifold, and it's about doing usual Morse theory on the infinite dimensional paths between two Lagrangians and looking to the real Morse function given by the real action functional. And here everything is complexified, everything is holomorphic. And so this holomorphic Floer theory picture has been just a formal picture, has been obtained independently by many people. I would just say that Kontsevich and Soibelman have a very big program related holomorphic Floer theory to many different topics, including some connection with DT invariants and with many other topics like deformation quantization, resurgence, many things that I will not talk about at all. So I'm just today presenting one particular aspect of the story, which involves trying to answer this question. And let me also point out that Doan and Rezchikov have started the development of the required analysis to make sense of this story. So each time you try to do some infinite dimensional version of Morse theory, you will, at the end of the day, you will get some kind of PDEs, and then you will need to do some very hard analysis to make sense of it and get something like enumerative invariance out of it. And Doan and Rezchikov have started to do that for holomorphic Floer theory. And so their work should be some of the first step if you try to make rigorous the kind of formal conjectural picture I'm going to present. Okay, so in more details, the input of this holomorphic Floer theory is some holomorphic symplectic manifold, so M with a complex structure I and some holomorphic symplectic form omega I. And I will actually assume that we have some hyperkeller structure on it, hyperkeller matrix. So you have a quaternionic triple I JK of compatible complex structure, and I denote by J theta, this linear combination of J and K. So it's important in this theory, from a hyperkeller point of view, there is a distinguished complex structure I, which play a particular role. This story is not symmetric under rotation of the twistor sphere of complex structures. So we pick L1 and L2, two I holomorphic Lagrangians. So they are holomorphic submanifold in complex structure I of middle dimension and omega I restrict to 0 over Z. And so given these two Lagrangians, we consider P the infinite dimensional space of paths between them. And we define W, some holomorphic function on it, obtained by integrating a holomorphic one form, which is a primitive of the holomorphic symplectic 2 form. So of course, the symplectic 2 form might not be exact. So this thing might not really be well defined. And so this W will be in general multivalued. And this thing will be actually essential for our later story. But from now on, let's ignore that. So you have this infinite dimensional space of paths, and you have this W, which is a holomorphic function on it. And then you can just run the Landau-Ginzburg story I was describing previously. So you ask what are the critical points of W, and they are the intersection points of the two Lagrangian L1 and L2. You can ask what are the gradient flow lines of these functions. So they are lines in the space of paths. So inside M, they are really planes, two-dimensional object. So they are family of one-dimensional object. And you get J theta holomorphic curves to get holomorphic curve in your holomorphic symplectic manifold for the complex structure J theta, which is this linear combination of J and K. And if you worked out what are the zeta instantons, so what are some of these kind of perturbed holomorphic curves in this space of paths, so you have two-dimensional family of paths, so you get three-dimensional objects. So you get maps from R3 to your holomorphic symplectic manifold. And if you work out what is the equation they have to satisfy, they satisfy the version of the Floer equation. So U is a function of three variables. So you have partial derivative with respect to each of the three variables, and you put the complex structure I in front of one and the complex structure J theta in front of the other. So counting holomorphic curves, the count of gradient flow line is something quite familiar in the context of either Gromov-Witten theory or Floer theory. But counting these three-dimensional objects is something which has been essentially almost has not been studied. And as I mentioned, Doan and Rezchikov started to do the analysis of this Floer PDE. So holomorphic Floer theory tell you should consider these various enumerative problems, count holomorphic curves, count solutions to this Floer equation. And out of this data, you should be able to produce the following things. If you have P and Q two intersection points of the two Lagrangians, you should be able to attach to that a vector space, HPQ of two-dimensional BP state of this infinite-dimensional LG model P and W. If you just consider L1 and L2, you should be able to attach to it a category, the category of branes of this infinite-dimensional 2D LG model. And finally, if you only look to your symplectic manifold and consider all possible Lagrangians, then you naively expect to get some kind of two category with object I holomorphic Lagrangians. So here, two category means that if you take two Lagrangians, what we attach to them is an ordinary category. And here, just a comment. So there are some expectations that we should be able to attach a two category to a holomorphic symplectic manifold called the Rosonsky-Witten B model. And basically, in this picture, what you are doing is that if you have two holomorphic Lagrangian, in the nicest possible situation, one is a graph of a holomorphic function over the other. And then the category in the Rosonsky-Witten story attached to that is a category of matrix factorization of this function. Here we do kind of a model version of that, where the category we attach to that is a Fukaya-Seidel category of this function. And it's likely that this category actually appear in some algebraic form in the work of people studying three-dimensional myosymmetry. Okay, so this thing is what holomorphic Floer theory should be about. And as I said, to make it mathematically precise, we'll need to work a lot about understanding solutions to this Floer equation. There is, as usual, with PDEs, you have problem of compactness of moduli spaces and so on. But for now on, I just take it as a formal picture. So now I come back to my original question. My original question was about n equal to four-dimensional series. And I wanted to recover the BPS spectrum out of a specific two-dimensional theory. And so now I'm claiming that you should do that from applying holomorphic Floer theory. So to this infinite-dimensional, two-dimensional picture. So to do that, I need to tell you one particular hyperkähler manifold M, and I need to tell you two particular holomorphic Lagrangians, N1 and N2, to run the holomorphic Floer story. So at this point, it's maybe not so surprising. I actually use the same letter for both. Then the hyperkähler manifold M should be the Seiberg-Witten integrable system attached to the 4D theory. Okay, so now what are the Lagrangians to consider? So my BPS spectrum, omega gamma of u, depend on a particular point u on the Coulomb branch in the base of the integrable system. So at least one of my two Lagrangians should depend on this point in the base. And I will do the obvious choice to take for L1 the fiber of the integrable system over this point u. So L1 will be the fiber, a torus fiber over the point u. And for L2, we'll take something which actually is independent of u. We'll take something I denote by S, which is a natural section of this integrable system. And on physical grounds, there is expectation that there always exists a natural section which can be physically defined as a boundary condition for the three-dimensional sigma model of target M, which is obtained from a four-dimensional background obtained by taking the product of R2 by a Seiberg geometry. So a Seiberg geometry is just some kind of interval across S1, where the S1 shrink to a point at one of the end of the segment. So you consider your 4D theory on this picture, on this four-dimensional spacetime R2 cross this Seiberg. And when the S1 is very small, this picture becomes R2 cross the interval. And the theory should be described as three-dimensional sigma model with target M. But because in 4D, the cycle was shrinking at the end of the interval, there is a non-trivial boundary condition. In this three-dimensional sigma model, this is a boundary condition is this section of S that I'm considering. So the story of deriving boundary condition from the Seiberg geometry is in particular in some work of Nekrasov and Witten. And so if you want to have some concrete mathematical example in mind, this M, you can think about it as a space of Itchin module space of X bundle, infinite singular systems. And in this example, this section is a so-called Itchin section, which can be described explicitly. So here is a picture that I'm talking about. I'm talking about M, this complex integrable system over the base B. M is some hyperkähler manifold. And inside it, I'm looking at two I holomorphic Lagrangian. L1 is a fiber of a specific point U, and L2 is a section. And I claim we should run holomorphic Floer theory in this particular setup. So we should consider the infinite dimensional space of paths connected L1 and L2. On this infinite dimensional Kähler manifold, you should consider the function W, which is a holomorphic action functional, and then you should run the story. So here there is something which sounds maybe worrisome, that the story might be trivial, because L1 is a fiber, L2 is a section, so they have a single intersection point, which sounds very little for what we want to do. So we are saved by the following fact that actually this infinite dimensional space of paths is not simply connected. And because this holomorphic two form omega I is not exact, actually this holomorphic function W is multivalued. So to get a proper setup, you need to work on the universal cover of the space of paths. And if you work out what is the fundamental group of this space of paths, it is exactly this second homotopic group of M relatively to the fiber. So it's exactly the space in which the BPS charges are living. So here is the first good news that what I'm talking about is not complete nonsense, is that in P there is single critical points, but on the universal cover, your function has really infinitely critical points indexed by a lattice, which is exactly the picture you expect, because you want to map these critical points to the possible charges for your four-dimensional BPS states, which live in the lattice. So on the universal cover, there is a natural action of the fundamental group. So there is a natural symmetry on the set of critical points. So I can fix this symmetry by just picking one of these critical points. I call it 0. And then from now on, I can identify the other critical points with element gamma of the lattice of 40 BPS states. Okay, so on this picture, P and P tilde are really infinite dimensional spaces. There is some holomorphic function on them. And on P tilde, this holomorphic function has infinite critical points in red on this picture, forming a lattice. And then you run, so the two-dimensional Landau-Ginzburg story in this infinite dimensional picture, you consider this gradient flow line in blue connecting these critical points, these holomorphic planes in red, which by holomorphic Floer theory translate into holomorphic curves and solution to the Floer equations inside M. And now here is the main claim or the main conjecture is that given n equal to four-dimensional field theory, on the one hand, you can look to H gamma of U, the space of BPS states of class gamma in a given vacuum U. So something which geometrically, if you have a geometric realization of your field theory from a Calabi-Yau threefold, this H gamma of U has to do with categorified DT invariants counting objects on your Calabi-Yau threefold. And the conjecture is that this vector space is isomorphic to the vector space that you obtain by running holomorphic Floer theory for the Seiberg-Witten integrable system. So for this particular hyperkähler manifold M, where you consider these two Lagrangian, a fiber and a section, and you consider the two critical points corresponding to 0 and gamma. So the point of this conjecture is that the two sides involve completely different kind of object. On one side, geometrically, you are counting current sheaf or special Lagrangians on the Calabi-Yau threefold. On the other side, you are counting holomorphic curves or solution to Floer equations into a higher dimensional hyperkähler manifold. And the relation between the two is that this hyperkähler manifold is a Seiberg-Witten integrable system attached to the 4D theory coming from the Calabi-Yau threefold. So this conjecture somehow is the main point of the talk. And somehow it is an answer to the question I was asking. So on one side, you have something which has to do with BPS states in the 4D theory, whereas in the other side, this holomorphic Floer theory has to do with some kind of 2D theory, some Landau-Ginzburg model, and some kind of infinite dimensional space of paths in this holomorphic symplectic manifold. And here is some actually simple looking, so maybe too simple, but probably forgetting many details. Here, the physics derivation of actually why this thing might be true. Yes. Okay. Is there a question? Yes.
Yeah, I have a question about kind of you make an analogy with 2D, and so then we had a Chakotay-Wafa, which means like 2D wall crossing formulas. But in the case of infinite dimensional space of paths, there might be pseudo-holomorphic disks with boundary on individual L1 and L2, unless your Lagrangians are exact and symplectic manifold is exact, which means that you should have 4D/2D wall crossing formulas in general, maybe not in your particular, for your particular choice, but in general, it's not just a kind of complete analogy with 2D. It's more complicated.
Yeah, so it's true that in 4D in general, you have the 2D, 4D story. And here I'm only restricting to the 4D wall crossing. So I'm restricting to the case where you do not consider the full 2D, 4D story. So indeed, the full story is not analogous to the 2D story. I'm only restricting to the 4D path, 4D direction somehow.
Yeah, and also kind of in your particular choice, because it's your proposal for 4D n equal 2. But yeah, in general, your holomorphic Lagrangian, they can intersect non-transversally, and then you have more complicated story than just a Morse theory. You have a cohomology with a sheaf of with coefficients in the sheaf of vanishing cycles of your potential, and so then kind of you'll have to give a meaning to this in infinite dimensional case.
Yes, yes. So indeed, it is like, as in
Yeah.
usual more theory, if you are not more, then you need to work more. And I am lucky that in this particular setup, they will just transfer intersection, but indeed, in more general, it's more complicated.
Yeah, but your approach, it's you will work constantly with infinite dimensional geometry. So kind of when you count gradient analogs of gradient lines, it's sort of counting of solutions to Kapustin-Witten or something. Do you have a finite dimensional model for
Yeah,
the
so
count?
the answer is no. So obviously, the ideal will be to have a finite dimensional picture, but I don't. So yeah, I'm just describing some answer to this analogy, which is infinite dimensional, but yeah, I don't know some finite dimensional version of it.
Okay, all right, thank you.
Yeah, thank you for the comments. Yeah, so the naive physical derivation is to, again, consider this geometry R2 cross a cigar. And on one hand of the cigar, I has a vacuum to be U. And in the interior, I ask my field, the total charge of my space, to be of charge gamma. And you expect the states of lowest possible energy there to be simply the BPS states of charge gamma. So the point is that if this cycle in this cigar geometry is very big, this geometry is not so different from flat R4 in vacuum U, charge gamma, in which you have usual four-dimensional BPS states. But now on the other side, if you shrink this S1 to a point, at low energy, you get some effective description, you get this interval, and you get this three-dimensional sigma model with target M. And so on this interval, you have two boundary conditions. One of them is a fiber over U, simply because it's related to prescribing the vacuum to be U. And on the other side, you have a section, because this section is a boundary condition corresponding to the tip of the cigar. And the fact that the theory was in class gamma means that you should look to maps with a corresponding homology class. So in other words, the answer to the original question, given the n equal 2 4D theory, how do you cook up n equal 2 2D theory, is simply by compactifying on this cigar geometry. You go from 4D to 2D, you need to compactify two dimensionals on something, and you just compactify on this cigar. And this two-dimensional theory, but it's the picture on the right, is equivalent to the 2D sigma model with target the space of paths in the hyperkähler manifold. And I will end pretty soon. Let me just mention that this cigar geometry and boundary condition in hyperkähler manifolds are being considered before, especially by Kontsevich-Soibelman and other people. But usually, the way it has been applied with an extra step, which is to do some half omega background around this cigar, to do introduce an equivalent parameter around this cigar. And here it is important that I am not doing that. Somehow, if you turn on this extra deformation, then it's related to holomorphic Lagrangian in M for different complex structures, essentially J holomorphic Lagrangians. And here I really want I holomorphic Lagrangian. So really, I do not want to turn on these extra deformations that people have been studied quite a lot. So there is a numerical limit which is connected to other works. So in the numerical limit, if you so the prediction is that the BPS indices, just the numbers, to be related to count of holomorphic disk in this geometry M, with boundary on the torus fibers, and it's related to previous work. In particular, Kontsevich-Soibelman, in which I have in particular this picture that this holomorphic disk should project to some graph in the base, which should be related to attractor flow trees. I guess on Thursday, there will be a talk by Boris Perlin more about attractor flow trees. And finally, let me mention that this picture is somehow compatible with the Gayot-Moore-Nalsky story in the following sense, that in mirror symmetry, you have some holomorphic disk instanton correction story, in which if you start with a Calabi-Yau manifold X, and if you count holomorphic disk in this geometry, you expect to be able to use this information to construct the mirror Calabi-Yau geometry Y. And I guess actually the next talk by Conan Langs and the talk in the parallelization by Ilya Argus are related to this story. And in this story, so if you apply it, when you Calabi-Yau is this hyperkähler manifold M, you expect that if you count holomorphic curves in M, you should be able to reconstruct the mirror to M. which because of this hyperkähler situation is essentially self-mirror. So we expect that if you count holomorphic curve in M, you should recover M. And on the other hand, Gayotto-Monaski tell you that if you know BPS states, you can also recover M. And so the fact that BPS states and holomorphic curves agree somehow makes the story compatible. Actually, it is the same story. And I will just end by application and further direction. So the main conjecture, you can view it as a kind of concrete test for mathematical constructions of holomorphic Floer theory. So I say it's not something well defined yet because you have to do some hard analysis. And I guess one question about finite dimensional model is because it would be much better to have a finite dimensional story and to avoid infinite dimensional picture. But still, if some people are able to do the required analysis and come up with some mathematical constructions, they might test it against something which are known. So in some cases, this space of BPS states or DT invariants, which might be known by some different ways. And the last comment is that there is a hope, which actually was the original motivation for thinking about that, is that this picture can give you some hint about the structure of 4D BPS states. In particular, in 2D, the wall crossing for BPS states, not just BPS indices. So the categorified wall crossing is kind of known in physics language, at least by Gayotto-Witten and Kahn and Moore, in which the wall crossing formula explains the fact that this category of brain does not change. You have some kind of local system of this category. And so you might hope that this kind of 4D, 2D analogy, which is slightly more than an analogy, which is kind of realized in this infinite dimensional setup, can give you some hint about the 4D categorified wall crossing. And in this picture, let me say something about the question mark in the analogy, which was about this category of brain. So the expectation is the category brain is related to the category of line operators in the 4D theory. It should be a categorification of the algebra of geholomorphic functions on it. And I will stop there. Thank you for your attention.
Thank you. Are there any questions? Okay.
Yes, thank you. So if I remember correctly, right. So if I remember correctly, that there's actually a one-parameter family of hyperkähler manifolds corresponding to this moduli space in after reduction on the circle, which is labeled by the radius. And in a large radius limit, the whole geometry is indeed determined by the four-dimensional BPS indices, by this GMN construction. So I was wondering whether in this large radius limit, you could actually prove your conjecture by computing the DT, the invariants on the Floer equation side and match them to those invariants which encode the geometry of the hyperkähler manifold in the first place.
Yeah, so maybe let's just talk about BPS indices. So it would just be about holomorphic disk inside the hyperkähler geometry, which should be matched to the, yeah, maybe in general, if you want the full correct answer, you might need the full thing. So the only thing I can know is that I can say that in some examples, it is known how to match this count of this kind of DT invariance count, BPS counts, and some algebra geometric well-defined version of this count of holomorphic disk. So something related to what we argued will talk in our talk, which is called log grammar Floer invariants or function grammar Floer invariants. In some classes, you can match these numbers, which really looks like the holomorphic Floer side, but in like this, in the only numerical limit, just count of holomorphic curves, you can really match them with DT invariants. And some of the only known kind of proof of this kind of thing is, which was maybe already hinted actually in the Kontsevich-Soibelman, in some of the Kontsevich-Soibelman paper, that somehow both will be controlled by the same kind of wall crossing formula, will be determined the same kind of scattering diagram. And if there's the same kind of initial data, you might hope to match one to the other. But I think it's fair to say that this Floer story, I think there is no non-trivial test, like at the level of spaces of BPS states. So really with like refined information, I guess there is not really non-trivial test of this proposal.
Thank you.
Any other questions?
So in simple cases, the base of the fibration, like the Hitchin fibration, would be contractible, would be a vector space itself. But that's not true in general, or at least it's not known. So does the topology of the base, would that affect your construction, your results, if the base is not contractible?
Yeah, so I have not been thinking so much about it. Yeah, so in most examples, the base is contractible, but I guess but recently physicists have constructed 4-dimensional series in which the claim is that the base might be maybe quotient by a finite group or something like that. And I did not check how exactly it would affect the construction. So one very basic fact is that in this computation of the fundamental group of the space of paths, to know that one is contractible, I mean, you kind of use that to show that it's reduced to this very simple thing. And so if you modify that a little, maybe you might need to take care of it, but I have not been thinking fully about it.
Any other questions? If not, let us thank the speaker again.